Welcome. So previous class we have discussed on number of signals, that is number of signals. How many signals are there in a particular molecule? So we have discussed about a homotopic, we have discussed about a diastereotopic, and we have discussed of enantiomers. So let's say if a molecule says you have, let's say CH3 CH2 Cl. Okay, so for these molecules how many signals we will get? So this is homotopic. So homotopic always it is not affected by asymmetric center, so this always give that one signal. So 3H will give one signals, and here we see that there is no asymmetric center, so this is enantiomer, so this will give 2H, will give one signals. So sorry, so total how many signals we will get? Total is 1 plus 1, that is 2 signals we will get in NMR data if this molecules is there. Okay, now another example, repeat that. Let's say we have that CH3CO CH3. So first we will check that POS. So POS is present here, it means that this and this are same, and this is homotopic, so 3H will give same signals, and since this is plane of symmetry is present, so both will give one signal, so 6H will give one signal. So if this molecule is present, then we will get the one signals. Okay, so that we have discussed in the previous class. Similarly way, if you have that, let's say you have that CH3 CO CH2 CH3. In this case how many signals we will get? So this is homotopic and this is also homotopic, so this is for but here plane of symmetry is not there, so this and this give different signals. So 3H will give one signals, and this 2H, this is no asymmetric center is there, so this is enantiomer, so 2H will give one signals, and again this 3H will give one signals. So total how many signals we will get here? 3 signals we will get. Okay, so this we have discussed in the previous class. Now we will discuss the chemical shift. So for today topic is chemical shift. And it is represented by this. Okay, so now what is chemical shift? It represents the positions of the signal. Position of the signal. So we have discussed that in previous class, that how many signals are present in a molecules. Now we are going to discuss that how many where that signals is located, or what is the positions of the signal. Okay, so previous class we have discussed that how many signals are there in a molecules. Now I will say that signals are there, then in which position that signals are lies in a NMR data. So that we will discuss today. So this chemical shift represent the positions of the signals, and it is in unit of parts per millions, that is ppm. Okay, so it is always taken in ppm. So now let's say we have discussed that, let's say this type of molecules we have the 2 signals. So if you look that NMR data, then how it will look like? So let's say this is that NMR data, and here what you take, that what type of instrument you are taking. Suppose if you are taking that instruments are there, 60 megahertz instrument, 400 megahertz instrument, 800 megahertz instrument. So this type of different type of instruments are present in the lab. Suppose you have the NMR of 60 megahertz instrument, that is low cost NMR, and here you get that less intense peak. And if you have little bit higher magnitude NMR, that is 400 megahertz instrument, on that case you will get a little bit good intense peaks. and if we have very big instrument like 1800 megahertz instrument, here get high intensity peak. So different NMR of different magnitudes are there. Some are smaller, some are big, medium, some are bigger. Okay, so that type of instruments are there. So here we'll take that magnitude of NMR. What type of NMR you are taking, means which NMR you are taking. Okay, so here that operating frequency, that is, or NMR taken. Okay, let's say you are taking on a 60 megahertz instrument. You are taking the 60 megahertz instrument. So in this case, how many signals are there? Two signals are there. So two signals will be appear here. Okay, so first one will be the reference standard will be first signals. This will be the reference standard. Always reference standards will be there. This is the reference standard. And in 1H NMR, we generally take that, we used to take TMS. Okay, so this is our structures like silicons, here 4 methyls. Why we will take this TMS, that we will discuss later. So for time being, I'm just saying that reference standard will be here first big. After that, these two signals are there, so two signals will be appear here. Let's say that these two signals will be here. Okay, I'm just taking as an example, just in the rough. So exact this type of NMR data that will be not same. I'm just taking that example. So suppose this type of things are there. So two signals. So two signals will be appear in like this. Okay, first will be the reference standard, then this, the two signals, or two signals will be here. Okay, similarly for this case, so whatever that you are taking that the operating frequency, whatever the NMR you are taking, suppose you have taken 1800 megahertz instrument, then 1800 megahertz instrument. After that, here these are the positions of the signals. Okay, so this is represented by the chemical shift. Let's say this is 1 ppm, and this is 1.5 ppm, this is 2 ppm, like that. So this is the chemical shift. Okay, so this is the chemical shift, and this is the positions of the signals. Okay, so two signals or two signals are there. Let's say here one signals. So here we take that operating frequency. Let's say we are taking 1800 megahertz instrument, then we will write here, then here we will write that signals, that positions of the signal, that is this, and here they will take in a ppm. So past will be that reference, then here that one signals are there, so one signal will be appear like this. Okay, similarly if it is that this type of molecules, here we have the three signals. So NMR data will somehow look like this. Here that what type of instrument you are taking. Okay, so let's say we are taking 400, let's say we are taking 600 megahertz. So 600 megahertz instrument will be here, and here we will write that positions of the signal, that is chemical shift, and that is in ppm. Okay, so past will be the reference 1 ppm, let's say. Then here we have the three signals, so three signals will be comes like this. Okay, so this way that, so we have that if three signals, the three signals will appear, one will be that reference standards, and this way that positions of the signals will come. Now that what the questions will come, that let's say we have, let's say that chemical shift ppm is ppm, this is equal to what you say, that precessional frequency, or I will write here this chemical shift, this is equal to precessional frequency that is taken in Hertz upon operating frequency, that is in megahertz. So this is the formula of chemical shifts. If we have that precessional frequency and if we have that operating frequency, then we can calculate the chemical shift values. So these values, this is the operating frequency, means what the magnitude of NMR we have taken. Let's say in this case we have taken that 60 megahertz instrument, so this will be the 60. Okay, if it is taken 400 megahertz instrument, then this is 800 megahertz instrument. If we have taken, then we can write here 800 megahertz instrument. So this is that operating frequency, means what the magnitude of NMR we have used. Okay, and so this is always given, this value is always given. And now they ask the chemical shift by giving this precessional frequency. If they give this precessional frequency, and they will ask the chemical shift value, and this value is always given. Okay, let's say here we have that chemical shift value is given 1.52 ppm. Now they ask that precessional frequency, then we can easily calculate that. That is, we see that ppm, that is chemical shift, is equal to precessional frequency, that is Hertz, upon operating frequency, that is megahertz. Okay, this one is taking that this is Hertz upon megahertz, this is ppm. So this one is given to you. Let's say this is 1.5 ppm and this is given 60 megahertz. Then we can easily calculate this value. Let's say this is x, so this x is equal to, we can say that 60 into 1.5, that is going to be 90 hertz. Okay, so you can easily calculate that. If any one value is given, then they ask that they ask to calculate this Hertz, or they may give this Hertz value and they will ask to calculate this chemical shift. So using this formula you can calculate the chemical shift values, or if they given the chemical shift, they ask the precessional frequency, then also we can calculate by using this formula. Okay, so regarding on that one, examples I have taken. Let's say example, if it is taken the 300 megahertz instrument and ppms is given. Okay, then calculate the precessional frequency. So for this value we can calculate the precessional frequency. So here that what you see that ppm is equal to Hertz upon megahertz. So now we want to calculate that precessional frequency, that is Hertz. So Hertz value if we want to calculate, then ppm into megahertz. Okay, so everywhere multiplied this value with this value, then we can calculate that Hertz value. So for 1.5 ppm, what the value, that is ppm is 1.5 into instrument is always 300, so multiplied with, you will get the value. Similarly for 3.2 ppm, we can calculate that, that is 3.2 into 300. Okay, similarly if you want to 5, for 5 ppm, that is 5 into 300 Hertz. Always unit will be always Hertz. Okay, so likewise we can calculate that if that chemical shift is given and operating frequency is given, then we can easily calculate the Hertz value. Also they will give that precessional frequency and this operating frequency, and they will ask that chemical shift, then also you can easily calculate it. Okay, so this is the one point, that how to calculate that precessional frequency, how to calculate that chemical shift and chemical shift because operating frequency is always given. So after this it is clear. Now the next point is that you see here that we have that two signals and we have done here two signals, but now I want to know that whether this one signal is because of this or because of this. So I want to know that this 3H we gave the one signal, so let's say 3HA and let's say 3HB. Okay, now I want to know that this is A and this B. So this A, because of A, which signal, whether it or this, whether this signal has come or this signal has come. So which signal is this? For this, which signal, whether it, whether this or whether this. So to understand that, we have shown that two signals, we simply write the two signals. Now I want to know that this is 3HA, so because of 3HA one signal has come, so this is A or this, which one? So for that, to understand that whether this is A or this is B, let's say this is B, or it may be this is A or this is B. So how we will identify that for this particular protons which signal has come? Okay, so for that what we look that let's say we have that CH3 CH2 Cl. Okay, so if you write here this C H H H and this is C H H and here Cl. Okay, so now what we are giving that, let's say we are giving some magnetic moments we are giving. So let's say we are giving that 60 or 400 megahertz, this magnetic moments we are giving, or let me take the some values, let's say 5T. I'm giving that magnetic moments to this, I'm giving this amount of operating frequency I'm applying to these molecules. Now let's say now what you see that here, this is always electron withdrawing groups, because here that electron withdrawing group is dominates, because this is highly electronegativity groups, so this will take electrons from this. Okay, so if it is taking electrons, then it will electron deficient, this is get something on delta positive charge, so it will take electrons from here. It means that this hydrogen is electron deficient, and let's say this is HA and let's say this is HB. So for this, that this inductive effect is distance dependent, so here that it take that electron is less. So let's say that electron density in HA is less, let's say that 2T, and let's say this HB, because this is inductive effect is distance dependent, so less electron it will take, so delta plus is less. So if it is less, then it will take very less electrons from here. So let's say it has that electron density at HB is, let's say that 3T, because less electron is it withdrawn from HB, so let's say it's a 3T. And now we are applying the 5T, we are operating frequency we are giving to these molecules 5T. Okay, so now that B effective is that how much you are giving, that is operating frequency, or we can say that this is B naught and this is the B induced. Okay, this is the B induced, this is B induced. Okay, so minus B induced. So B effective equal to, so how much you are giving, that is 5T, and how much induced for let's say for B effective of HA, for that how much it is induced, that is 2T, because that how much electron density it has, that amount it is induced, so 2T will be there. Okay, so B effective for HA will going to be 3T. Similarly, for if I take about of this B effective for HB, that is B naught minus B induced, so B naught is how much, 5T, because same magnetic field we are applying, so this is 5T, and this is how much we have, less electron it has withdrawn, so it has the 3T, so total is going to be 2T. So B effective for HB is equal to 2T. Okay, so now this B effective is directly proportional to chemical shift. Okay, so this, if B effective is increases, then chemical shift will be increases, or this is precessional frequency. That is so if B effective will increases, then chemical shift value will be increases. Okay, so now also we can say that this chemical shift delta H is indirectly proportional to electron density. So if electron density in an atom is high, then the chemical shift value will be decreases, or electron density is directly proportional to the chemical shift, sorry, indirectly proportional to the chemical shift. So from here what you understand, that for this the HA and HB, what we see, that this HA HB HA has 3T, this is HA has 3T, and this HB has 2T. It means that this B effective is directly proportional to chemical shift. It means that chemical shift of B effective HB is 2T, and here that chemical shift of HA is 3T. It means I say that chemical shift of HA is greater than chemical shift of HB. Okay, so where you see that in this case, wherever that electron withdrawing group has attached, on that case the chemical shift is increasing. So here electron group is attached to near to this, so this HA has the high chemical shift. So from here I can say that electron withdrawing group will desilidate and it will give that high chemical shift. If we have the electron donating group, then that will silidate the atoms, and it will give that low chemical shift value. So from here it is clear that if you look this atoms, so this will be electron withdrawing group, give that desilidate, and you have the high chemical shift values. So high chemical shift value means here we have that two, I'm taking that, here we have that two signals, and this this 2H is near to electron withdrawing groups, so it will be the d-shielded, means high chemical shift value. So if it is B, then this will be the, from here this is high, so this one is high, so this will be the Hb protons, and this will be that shielded, so this will give the low chemical shift value, so this will be the HA. Okay, so here that one signal, so one signal so will be here. Similarly, we have here three signals. So this one we will while we will discuss factors affecting chemical shift, then we will discuss that where the positions will come clearly on that case. Okay, so this is how that where that locations, where the positions of a signals, how it is depend on that whether electron donating group is attached to the atoms, then how that chemical shift is increasing, and if electron donating group is attached, then that electron chemical shift value is decreasing, that we have discussed now. So now we will go to the next point, that is let's say we have said that in a, here we have said that one reference, standard reference is taken. Standard reference. Okay, so for 1H NMR, let's say TMS is taken. So let's say you are taking that 400 megahertz instrument, or we will discuss this in the next class. So today up to this, thank you.